last time we were talking about coordinate systems. So what I did was I tried to give you some ideas what coordinates are in general, and those are procedures that give us some sorts of values that we can map the points in a space into a set of numbers that then we can work with and we can formulate problems with. And we kind of started from a very general notation and then looked into Cartesian coordinate systems. So before getting started, since it's been a while, I assume that you may have forgotten one thing or two. Let's just very quickly remember what gradient was. How did we define gradient for a scalar function of a point f? Do you remember anything about the relationship between differential and gradient? We kind of said, let's forget about coordinate systems. If you write the differential, let's say for a scalar valued function of points, how does this relate to gradient? Does anyone remember?
It's the gradient times part of the gradient
in independent variable. Excellent. And we kind of said that gradient also is a function of delta x, and typically it is evaluated at a specific point, right? It's too small. One class we missed, I forgot how to write it. Yeah, exactly. And just very quickly, and this is also, of course, a function of delta x and x0. I just don't write it. And let's remember that what kind of an object is the gradient of f? What kind of an object? It's a vector. It's a vector field. How about if we had a vector valued function very quickly? Would you be able to write it on your own? If we had the vector function v, what did we say the gradient is in that case? It's a tensor, and basically the same thing. And we are not talking about coordinates here. But then I talked about coordinates, and then I defined a function called a coordinate function, something like that, which maps points in the Euclidean pointer space to scalars. That's what we learned about coordinate function. And now, do you guys remember the gradient of this function? We also talked about it, and we said that just like before, you could say, well, you know exactly how to get the gradient of anything. So this is a scale valued function of points, and just like before, you could calculate the gradient. And at the very end, we showed that in Cartesian coordinate system, what do we get when we calculated this gradient? The basis vector, right? So then we concluded that these form an orthonormal basis. And we also saw that because these are just the unit vectors for the basis, they are also constant. This is where we stopped last time. Now things become much more interesting today. So last time it was all general, a little bit hard to probably follow, very general statements. Today everything becomes more specific. So we want to now calculate the gradient of functions, the scalar valued and vector valued functions in Cartesian coordinate systems. And the nice thing is then you will say, wow, you already knew that, but we kind of took a different route. I gave you the general formulation, and then we kind of see how things look like in Cartesian coordinate systems. So let's do it, what I just said. Let's start with a function. Let's change this to blue, maybe. I'm going to stick to it, if I remember. Okay. Let's consider a function, a scalar value, just like before. So I put this wave here. I consider f to be and a scalar valued function of which is mapping the points into R. And I just reviewed this for you, that you all told me that you all know what the gradient is. Now, how do I write this in coordinates using the coordinate system? Because typically this is not how we have the functions. Typically our function is actually tied to some sort of coordinate system. We want to study an object and we have to choose a coordinate system. It's actually pretty easy. So this function is a function of points, and these points for each point we have a set of values that we called are the coordinates of that point. So it looks like it's like a function of a function. And now it's very easy to calculate the differential, right? We know how to do it using chain rule. So we say, okay, so if I calculate the partial derivative with respect to, or derivative here with respect to psi I, then I can get a differential using that. And the nice thing is we already know how to calculate the differential of the coordinate function. So we use the gradient definition again. And look at what we all agreed on above and below with 1 and 2 asterisks. So if we compare them, I hope that you can easily see that the gradient would be basically the derivative, partial derivative with respect to psi I. And this is general. So the nice thing is now we can use it for Cartesian or polar coordinates. This is what we have. But in Cartesian, this becomes very, very simple, right? Because what did we say before? We said that in Cartesian coordinate system, the gradient of the coordinate function, they form an orthonormal basis. So what can I say about the components of the gradient of function f in Cartesian coordinate system?
Its derivative is independent in terms of its components.
No, maybe that was like a long sentence with a lot of function and gradient in it. So let me rephrase it. So we said that now you have this form. We said that gradient is an object. is a vector, right? And in Cartesian coordinate system, those delta psi i's, what are those?
Basis.
They are unit vectors. They form an orthonormal basis. This is important. So now let me change my question to make it more clear. What can I say about the components of this vector gradient in Cartesian coordinate system? Exactly. If this is not very clear, I use the orange trick. I told you always, if I write something in orange, it's just something that you should remember. So remember that we talked about a vector in an orthonormal basis like that. Okay, compare the two. If the basis is orthonormal, it's very easy to get the components. Those coefficients are the components. So now, if I ask you this question again, I hope everyone sees that the component of gradient is nothing else but the partial derivative with respect to the coordinate I. And this is what John said earlier. Yes? And that's something you have seen before. When you think about gradient, I'm sure all of you think Cartesian coordinate, and you kind of think about these partial derivatives with respect to x, y, and z. Raise your hand if this is not true. Right. So this is the same thing as before. Now the nice thing is you will see when we talk about polar coordinate, I use the same formulation, and I just use the delta psi I in polar coordinates, and then we have it. Because that what is in the box, in the blue box, is general. Okay. But then we can very easily, whatever coordinate system you want, you can derive what you want in that coordinate system. So let me just write this down. So this, and also, I mean, needless to say that when you have these double i's, this implies summation. And we are using index notation. You did the homework, now you are all expert. You know how these things work. So the point here is to remember that delta psi I, it forms a basis no matter what. But if you have Cartesian coordinate system, it forms an orthonormal basis. And that makes everything easy. Now, of course, you see what is coming. This was a scalar valued function of points. Now we want to do the same thing for the vector valued function of points. So just exactly the same thing. So let's just do the calculations. Any questions? So now consider having a vector valued function of points, and I write it like this. So the question is, now how do we get, in terms of coordinates, how do we get the gradient of V? Remember that this gradient is what type of an object? It's a tensor. So we have used I here, I've used P for no good reason. So I do exactly what I did before. So saying that, well, these x's, it's very hard to map them anywhere. Yes. What do you mean? Oh, this is just VI. These are just the components of this vector valued function. Oh, yes. Yes, thank you. This was, of course, intentional, as always. It's just to make sure that, and this time Tony is the winner because he actually could see it. Yeah, you need to really be careful. Sometimes I say things, I mean something else. I'm trying to be very careful, and I write. So you please check always, and I'll be happy to change things. So now, again, we use coordinates to be able to express points. So we do exactly the same trick. And what do we start with? With differential, just like before. So we say, okay, the differential of v, you all know how this goes. And now, because vi is a function of psi p, then we need to use partial derivatives. Not make any mistakes. And what is the differential of psi p? So we talked about it. Now everyone should know this by heart. So I just substitute. And for the reasons you will see, I kind of move d psi p and the partial derivative around. I'm allowed to do that. Try not to make any mistakes here. It's nothing. I'm just writing the differential, just saying, okay, x, I write it in terms of coordinates because that's what we do in practice. And now, how does the gradient, I want to see how the gradient would look like practically if I want to actually calculate it. Okay, so now I need your help. I told you this is a tensor. Do you see a tensor? Look at things carefully. Someone is, Nike? You don't see any tensor, huh? No? Do you see any tensor product? Anything which looks like something you have seen before? It looks like I need to use the orange color again. Just to make sure. So again, this orange is when, remember this tensor acting on a vector, and I don't expect you to remember this, but not remember exactly, but kind of have some idea, something like this. Now, with that, try to write down what we have here in terms of a tensor product. Now you see what is going on, right? The gradient of psi p, this is what kind of an object? It's a vector, right? Delta x is a vector, ei is a vector, and the partial derivative of ei with respect to psi p, that's also a vector, right? Everything. So you can very easily see that you can turn this into a, you see a tensor product. So, should I let you write it? Yeah, why not? Late in the afternoon. Kind of, yeah, but there's no point in trying. Like a mental gym, mental gym. So I write it quietly, like always. You write it for yourselves. Look up and see if it's correct, or if I have made a mistake. That's also possible, right? Yours looks a little bit different. Maybe you didn't factor out delta x, but that's not a. And of course, it should be clear why I'm doing that, because what I was interested in was the gradient. Have I made any mistake? Prabha, confirm. Great. So we have the general expression for the gradient. Let me write it because so this VI is the component of the vector field. So it's scalar. This is the general formula. Now, I want to give you something fun to check. Try to see how it looks like in Cartesian coordinate system. So the question is, how does this look like now? It looks kind of very unfamiliar. You have this outer product that I know many of you don't really like. But what happens if we try to look at the special case of Cartesian coordinate system? Try to see if you can get the expression. Work with your neighbors. If you are sitting see what happens if you are looking at coordinates or if you are looking at Cartesian coordinate system. This is a very general formulation. So now, how does it look like? When later in the course, we look at everything in the Cartesian and polar in this class. Maybe later on we want to work in other coordinates. But I want you to go from here to the center. With Cartesian coordinate Ask me questions, because then I know what you are studying. So, some hints. I think everyone can do some hints. What do we know about Cartesian coordinate systems, the basis vectors? Last time I introduced them. What did we learn about them? One thing we learned was they are constant. 60%. I see some happy faces. The second thing you know is the gradient of the coordinate function in Cartesian coordinate system. What is it? It is just one. What was to be the gradient of coordinate CP? What is that? It's just EP. That's all you need to know. So one thing is EI. Now we forgot about the generality. We are going back to our familiar cozy coordinate system, Cartesian. We know that the vectors, the unit vectors, are constant. When something is constant, when you take partial derivative, what do you get? 0. So the second term is 0. And the first term, in the beginning I reviewed for you, and we saw it last time that the gradient of the CP is just EP. Okay, we didn't use P before, it was I, but doesn't matter, right? It doesn't matter. Now we know. So if I want to write this, and some of you have already done that, I saw. You can just write it like that. And now I have to go back to what you have seen this kind of a form before. What are you looking at? A tensor. What is this which is kind of multiplied to this by this tensor product? What did we call this? Say it again. Exactly. So maybe necessary, right? So remember this. Remember? So if we have that, then I think it's fair to say that the component, now in this case is IP. Sorry, I use IP here, but right now we know what you are more familiar with is something which looks like that. You all have seen this before too. At some point in your life. I don't know exactly where have you been or what you've been doing, but you have seen this. And I know that. Okay. Now the nice thing is, when we go to polar coordinate, I don't go through anything. I just take that equation and then we just talk about how it will look like in polar coordinate. So we forget about everything else that we said before. We start from the general explanation. Any questions so far? So now I've kind of told you everything I wanted to tell you in Cartesian coordinates. At the end, I'll add to the tensor notation a little bit, but we can wait there. So let's just move to polar coordinate systems. So, polar coordinate systems are useful when, for example, you have a geometry in your problem where it would make better sense to use these kinds of coordinates. So be ready to download a lot of information that we talked about before when I was explaining this in some sort of a little bit of general terms. So we said that definition of a coordinate system is like a procedure. So I have to give you a set of procedures to define how we set up this coordinate. And I tried to use a similar method here. So just like before, we start by finding one arbitrary point. So I just pick an arbitrary point. And normally we call it O. You all know this is going to be the origin. And then the second step is I pick the point I want to represent in this coordinate system that I'm about to define. I take it. Now I want to define the coordinates. One coordinate, I define it very simply. I said, okay, this coordinate is nothing else but the distance between x and O. And we define the distance. We know that in Euclidean pointer space we can have lines, distance, and everything. So I just say, okay. So I take O. One of those numbers, which we call coordinates, will be just the distance. And you are probably familiar that we normally show this with R. We are not done. We are in two-dimensional space, so we need how many coordinates? We need 2. So the second is I need to draw a circle around centered at O. But this circle is not an ordinary circle. It also has to have a direction. So, and the direction I take it to be counterclockwise. So I draw this circle. And I'm not done yet. I also have to draw one arbitrary line which passes through O. Which sometimes we call it reference line. And you know exactly what I'm getting to, because I want to also, I need, for the second coordinate, I just calculate the angle from that reference line to the line that connects O and X. And we are basically done with that. So theta is measured from reference line to, and the direction is indicated by the direction of that little circle that we have. So now we got the 2 coordinates that we were looking for. So the first one we call it radial coordinate. And the second one we call it angular coordinate, and I just use theta. And you saw before that for calculating the gradients, one thing which was very useful was this gradient of psi function, the coordinate function. So it would be very useful to have that for this coordinate as well. Okay, so here is our reference line. So I want to find out a little bit about these gradients of the coordinates now in this coordinate system. We learned that we have the distance and the angle as the two coordinates. Now my question for you is, what are the coordinate lines here? Remember, in Cartesian coordinates, remember coordinate lines? It is when you take one point and then at every point you can pass as many coordinate lines as the dimension of the space you are in. So in Cartesian coordinates, looks like the orange. If you remember, in Cartesian coordinates, we also had this O, and then we had x0. And do you remember anything about this L1 and L2? Right? I asked you to figure that out, and then we saw that the gradient of the coordinate function are tangent to these lines. So now, what are the L1 and L2 here? No, but what are they? Exactly. So, what is L1? What is L1? Go back in your notes if you don't remember. The reason I spent so much time on those was because I didn't want to repeat them here. So look back and see what was L1. L1 was the line where the first coordinate could vary, right? The second coordinate, you would fix it to be exactly like the coordinate of the point that you are looking at. So in this case, it would mean that I'm looking for a line, a curve, let's call it a curve, where the first coordinate can be the coordinate of this point x0 plus minus, and the second coordinate has to be exactly theta. What kind of curve is that? It's just a straight line, right? I think last time I used this color. So any point, so if you don't remember, no problem. Any point you take on L1, it has exactly the same second coordinate. It has exactly the same theta as x0. But its distance from O, which is the first coordinate, can be anything, right? So that's the first coordinate line. And the second coordinate line should be a curve where its distance from O should be exactly r, or this distance that we have. But the theta can be anything. What is that curve? Circle, right? But not any circle, right? A circle which is crossing, which is passing through x0. It's centered at O. I'm not repeating too much here. And look at any point here. If you take any point, the distance to O is the same as x0, but theta can be anything. The second coordinate, so that's why. Now the nice thing here is that, or the reason I need it is because now if I want to know how the gradient of psi 1 and 2 look like, I can just draw the tangent on these two lines at that point, right? So let's do that. And then the direction of the tangent here, remember we chose the direction. So the direction of these two guys. And in polar coordinates, we don't use 1 and 2. You typically call this one r and this one theta for obvious reasons. Okay, so now in Cartesian coordinate system it was easy. The gradient was exactly equal to the unit vector. Here it's also easy, but it's not exactly that. Without showing you the proof of why it is like that, looks like I need to draw this again. Just bear with me. There's no way I can make the full circle right here, so yeah, this is a full circle, so I don't know how to do it. So it turns out that the unit vectors are parallel to the gradients as we would expect, but they're not exactly equal. So the gradient of the first coordinate is just the first unit vector, and the second one is just there is one r. And ER and E theta, they are orthonormal, as you can see here. And one other important thing to remember is that, and I use a color, is that unlike in Cartesian coordinate system, these are actually a function of x. They are not constant anymore. So maybe I write that they are not constant, because this is so in comparison, in Cartesian coordinate system, the gradient of psi I was just EI, constant, nice. I could easily show you. I debated with myself whether to show you or not. I decided not to. Why those two amount to ER and 1R E theta? If anyone is interested to know why, please come to my office, I'll show you. Just send me an email and I'll show you why it is like that. But I decided not to do it in the class. It would take some half an hour, I think, to show you. But it's not very difficult. You all have the tools to be able to show it. Now that we know this, let's go back and try to write the gradient of f in polar coordinate system. Now, go back to your notes from today. Write the general expression for the gradient, the general. Of a scalar valued function f if you can't write it down, I have to see 3 correct answers. uniformly geometrically distributed in a class. Not uniform distributed. Okay, if you have it, start writing. I've seen 1, 2, 3. So you have it. Let's start with the scalar valued function first. This is general, right? No strings attached to this one. Now write it in polar coordinate system. How many terms do we have? 2. We are in 2-dimensional space. So instead of 1 and 2, let's use r and theta. This is a summation. Right? And now all I have to do is to substitute the relations for the gradients, the relations that I didn't really show you, but I hope. So typically you just say R, it's much easier. Compare this to the Cartesian coordinate. This is something that you all think about when you think about gradient. The formulation is general, but you see that in polar coordinate it's not exactly that. It doesn't become just simply the partial derivative with respect to that particular thing. But we derived both using the same formulation. So I hope you see the beauty in it. I know it's late, but still, I mean, looks beautiful. You should be excited because I'm sure you guys also have seen this in some courses before. It just came from somewhere. You saw it on your notes, it appeared, and then you had to just plug things in, right? I guess so. You just need to download some memories. So I think I'll stop here. Actually, I made good progress. I just have a little bit left. So as we made the deal that I continue that, record it, write the notes as if I was in the class, and then you can go and look at it. And don't be so sad because that would be an extra work for you. The good news is that on Thursday I need to let you go a little bit earlier because I'm organizing a professional meeting here and I cannot miss it because I'm organizing it. So I will let you know, I will have to let you go a little bit earlier. So kind of that should cancel out a little bit in terms of time. So don't have any harsh or hard feelings about this, okay?